Hello everyone, good afternoon, good evening or good morning, depending on the part of the world that you are. First of all, I would like to say thank you for joining us today and welcome to this amazing saga. Today we are going to host one more episode of the Energized Saga, and this episode is hosted by MWE, Mozambique Women of Energy, in partnership with Mozambique Gas Summit. I'm Márcia Mabilane, and I will be the moderator of today's session. I'm a chemical engineer, and currently I'm working at Technip Energies Mozambique as a process engineer, and I'm also member of MWE. For those who are not yet aware or familiarized with MWE, MWE is a platform, is a group of passionate professionals determined to work together to identify areas of action and empowerment to change the narrative of Mozambique in order to contribute to the sustainable development of our country. We target gender equality and equal access to energy. Most importantly, accessible, reliable, and affordable clean energy. We want to empower the female future Mozambican leaders, and our focus is to inspire, empower, and support the young professionals of the energy sector to help them to create an impact both local and internationally. And to achieve this mission, we hold ourselves in 4 pillars, which are connect, lead, think, and build. And the Energized Saga is part of the build pillar. We aim to build capacities to young professionals in order to ensure that they have a smooth insertion in the practical and the work environment. We are aware that the information regarding to the LNG and the oil and gas industry are not available in easy sources. So we created the Energized Saga to make sure that everyone have access to information like this. Before we get started to our episode, I would like to do some housekeeping. The first point is that the meeting is being recorded. So if you miss something during the presentation, during the meeting, you can watch it later. It will be available on our YouTube channel in next week or 2 weeks later. The second point is that our session will be divided in 2 parts. The first part will be the presentation, and the second will be the Q&A session. I would like to highlight that below on the screen of your mobile phone or your computer, you can find the Q&A button and the chat button. So if you want to make questions, I advise you to use the Q&A button. And if you want to make a comment or give us a suggestion, you can use the chat button. By default, all the attendees are muted to avoid disturbance during the meeting. Today's episode is the continuation of the part 2 of the Energized Saga. That is the EPCAC part that stands for Engineering, Procurement, Construction, Installation, and Commission. And today, we are going to learn more in depth about the EI part. And the topic for today is subsea installation. To approach this topic, we have a special guest that is Michael Pontes, and he will follow up and make the presentation. Thank you, Michael Pontes. The floor is yours.
Good afternoon, everyone. I hope you can see me and hear me clearly. My name is Michael Pontes. Thank you, Márcia, for introducing me. I am a subsea engineer with Technip FMC, and my field of experience and today's presentation is focused on the subsea engineering and subsea equipment. This is the equipment that is installed on the seabed to make it possible for us to extract the hydrocarbons, in this case, oil or gas, in Mozambique, gas. So, as I was saying, today's subject is subsea installation. And I'll show you briefly the Mozambique LNG subsea field, just as an introduction, what a subsea field looks like. And then I'll show you a brief video that will give you an overview of what the subsea field looks like, the various equipments and the well, and how we extract the gas, process it, and how it comes back up to the surface. And then after that, I will get into each a bit of it of each equipment, talk about how we drill, how we find our wells, and then our subsea completions equipment, our Christmas trees, tubing heads, manifolds, our drill centers, PLETS, PLEMS, and then finally subsea controls. So a little bit an overview of the equipment that we install subsea, not all of it because it would be too much, but these are the major equipment that we install subsea to allow us to safely extract hydrocarbons. So this is what the Mozambique LNG subsea field looks like. I'm using it as an example and for its relevance to us here in Mozambique. We can see the onshore LNG facility that will be constructed in a fungi, and it is connected to the subsea field far offshore. What we see here is several Christmas trees, manifolds, flow lines, various equipments that are going to produce the gas and then allow it to flow back to shore to a fungi. Then what we see here on the surface are various vessels that are involved with the installation of equipment and different operations that we do offshore during the installation and during the lifetime of the field whenever several operations need to be done.
The subsea system encompasses all equipment between the reservoir and the host facility seen on the far right of the screen. It is quite literally the conduit through which hydrocarbons are safely transported from their source beneath the ocean floor to a facility where they can be processed. Subsea developments can stretch across tens of miles of seafloor and be located in water depths up to 10,000 feet. To best understand how each component in the system works, we must begin near the source. As you can see, we are now beneath the seabed looking down at the reservoir, which could be up to 5 miles from our current position. Reservoir size, shape, and composition will play a significant role in the design of the subsea system. In order to move production from the reservoir to the seabed, we must drill and complete a subsea well. The subsea well is comprised of a number of concentric casing strings which are drilled and cemented into place. Once these casing strings are in place, the production tubing is installed at the center of the well. This is the final conduit through which production is transported to the seafloor. Of the 20 to 30,000 feet of...
So just to recap what we just saw, what we're looking at here now is the reservoir below the seabed, and this could be many kilometers below the seabed. And to reach it, we need to drill these wells to get down to it. And these wells will guide the gas or the oil up to the surface. And here, once they reach up to the surface,
production tubing is
they will be processed by the Christmas trees.
Production tubing
I'll allow the video to continue.
Is installed at the center of the well. This is the final conduit through which production is transported to the seafloor. Of the 20 to 30,000 feet of casing and production tubing, only 8 to 12 feet of the well actually protrudes above the seabed. This top section of the well is known as the wellhead and is where the weight of each casing string is suspended. Now that we have a conduit, we need a way to safely control the flow of hydrocarbons up and out of the well. This control is provided by a device known as the subsea tree. The subsea tree has several critical roles within the subsea system. First, it is our primary line of defense when containing production from a subsea well. The tree is equipped with gate valves designed to shut in the flow in the event of an emergency or for a planned shutdown within the field. Second, the subsea tree allows the operator to regulate the flow of oil and gas from the well through a device called the subsea choke. And last but not least, the tree is equipped with numerous sensors, meters, and chemical injection points which allow the operator to monitor and condition the fluid as it leaves each well. Together, these functions make the subsea tree one of the most critical components in the subsea system. Most subsea fields have multiple wells drilled within a common area known as the drill center. In most cases, wells drilled within a drill center will have their production commingled locally and transported back to the facility through one or two larger diameter lines. This commingling process is performed using a device called a subsea manifold. Manifolds come in various shapes and sizes depending on the number of wells, production flow rates, and the number of flow lines used to transport the commingled production back to the facility. Because manifolds are heavy and not supported by a subsea well, foundation structures such as mud mats or suction piles must be used to support their weight on the soft seabed. To connect each well to the manifold, a device known as a well jumper is used. The well jumper is a short section of rigid or flexible pipe fabricated and installed after the tree and manifold are in place. The well jumper is equipped with a connector on each end which accommodates remote makeup of these connections. As shown here, most subsea connection systems are ROV operated due to the extreme depth associated with most deepwater developments. In order to control, monitor, and supply power and chemicals for most equipment in a subsea system, an umbilical termination assembly is commonly used. Equipment such as trees and manifolds often need electrical power for sensors and meters, hydraulic power for valves and chokes, and chemicals for flow stream injection. The supply of these commodities is provided through an umbilical and distributed throughout the field from the umbilical termination assembly. Steel flying leads, shown here in blue, transport the hydraulic fluid and chemicals. Electrical flying leads, shown in red, transport the power and communications. Without subsea controls, the subsea system could not function. Once production leaves the drill center, it moves into the horizontal pipeline section of the subsea system. The transition from vertical jumper to horizontal pipeline takes place at the pipeline end termination assembly, also known as the PLET. To the right, we have inline Ts, which are pre-installed single well tie-in points for satellite wells located outside of the major drill centers. These satellite wells may be part of the initial production profile or could be installed in a future phase of the development. These are the basic building blocks of a typical subsea system.
I hope everybody could see the video well, see and hear the video. That was a brief introduction of what a subsea system looks like. And next, I will get into some more detail of each equipment that we just saw. So this is what we call a drill center looks like. We saw earlier in the video, we saw the Christmas trees where the that sit on top of the wellhead in the well where the gas comes up from, and from there, the hydrocarbons will flow through a jumper onto a PLET and to a manifold. We see here the PLETs. The reason we need these PLETs is to, although in this image the distances look relatively short, this could be kilometers apart. So it wouldn't be feasible for us to have a single pipe, say, connecting the Christmas trees to the manifold. So we have these PLETs in between that just break the pipe into different sections, and they allow the hydrocarbons to flow through. These are just the flexible jumpers connecting the Christmas trees to the PLETs. Sometimes these could be rigid jumpers as well. 10-inch flow line that allows the hydrocarbons to flow between the PLETs. A 22-inch trunk line that will carry the hydrocarbons back to shore. An inline T that will connect this particular manifold to the trunk line in a say as a T junction. Think of it as a crossroads. And our umbilicals, which bring controls from either a vessel on the surface or from shore. And these umbilicals bring hydraulic power, electrical power, and different chemicals to the subsea field that are required. Once the umbilical reaches its location, it is terminated at what we call an umbilical termination assembly. And from there, the hydraulic and electrical power is distributed by these flying leads. And from there, it will go to the Christmas trees and to the manifolds. Just to show the difference, this is the Coral South field. Instead of the oil and gas flowing back to shore. In the case of Mozambique's case, it'd be a fungi. The produced hydrocarbons flow up from the wells, up these risers, onto the floating LNG vessel. This will be a very large factory vessel that hopefully will come by sometime early next year. And all of the gas flows to the vessel, is processed at the vessel and shipped from there. So next we'll talk about how we find the oil and then drilling. So how we find the oil offshore. Seismologists will use advanced survey ships to build a map of the formations below. This is done by using sound waves that are produced by the ship that are sent downwards towards the seabed, and they reflect off the various rock formations and the reservoirs down below, reflect off and are picked up by these hydrophones. These hydrophones will be on a very long cable that is dragged behind the ship. It's very sensitive, and they will pick up these sound waves that will bounce back up from the seabed, and they will tell seismologists what is happening down below. And in this way, we're able to find, or at least estimate, where the oil is and where we should drill. Once we have a rough idea of where these reservoirs are, we will then drill to make sure that of the oil that is there. Until we actually drill down there, we are not sure what oil is there or what gas is there or the quality of it. So after the seismological survey, we will drill exploration wells down to the reservoir, and we will take samples of that oil. So when the oil is found, further studies are done to determine the reservoir size and shape. And this is still through seismological studies and through drilling. We'll look for seabed hazards, look for drilling limitations in our subsea and in our drilling path in the ground, and we'll find the number and location of the wells that will be required to drain the well. We want to extract as much gas as possible from these wells, and so this study will help us understand where we should drill to get that oil or gas. And we see here in this image, we can see a reservoir, and we can see where locations where there is gas and where there's oil and where there is water. And these are different wells drilled to different locations on the reservoir to extract oil and gas, and even to inject water. Sometimes we inject water into the reservoir to try to push up the oil so it can make it easier for us to extract it. How we drill. So with the seismological studies done, we need to drill our wells to reach the reservoir. And offshore drilling can be done by different types of drilling rigs, depending on the water depth. So with shallow waters, we will typically use jackup rigs. These are towed out to sea, and they sit on the seabed, are jacked up to a suitable height, and from there you can drill. But when we're going to drill in deeper waters, then we possibly use semi-submersible rigs. These can travel on their own, under their own power, and they can drill down to extreme depths. However, both of these ships are not suitable for long journeys across the ocean. So modern rigs look more like this. This is an example of a drill ship. And besides that very tall tower we see in the middle, it's almost like a normal large vessel. And these can sail across the oceans to any location on the planet and drill to very, very extreme depths. Today, we're drilling to over 2,000 meter water depths. In the case of Mozambique, we'll see some wells perhaps as deep as 1,500 meters. So how do we drill the well? We're in the middle of the ocean, and we have our well there, and we want to start drilling. So we want to reach the reservoir below the seabed. On the left-hand side, we see our drilling rig position over the location we want to start drilling, and what the finished well might look like. Due to the depth of the reservoir and the complexity of the formations we must drill through, we must drill in stages, pausing to secure the well by installing these various steel casings that we see here. Without the steel casing, the well would not survive this crushing pressure and would cave in. As you can see, each casing that is installed, the diameter of the hole becomes smaller. We started with a 36-inch hole up here, and we might end up with a 9-inch hole once we get to the bottom. The reason for this is as we drill, we first start with a 36-inch casing, and we will reach perhaps 100-meter depth with that first casing. And from then on, we will have to install a second casing into the hole to secure it, but that casing has to be smaller than the 36 kg casing, and so forth. So as we drill deeper and deeper, the hole gets smaller and smaller until we end up with perhaps a quarter the size of hole that we started up on the surface. So to begin, we first need to locate the well on the seabed. We do this by drilling a 36-inch hole and installing the first and largest steel casing called a conductor or low pressure housing. This is what a conductor typically looks like. This is just one section, but once it's on the rig, several sections will be joined together and it may make up 100 meters or more length of casing. So this first hole is drilled through the soft seabed to just perhaps 100 meters, depending on the seabed conditions, until the harder rock below is reached. So down up this top surface here of the seabed is only the very soft sand that we have on the top, and then below that is harder rock. So the conductor housing is only installed until we reach that harder rock. This first step is also called spudding. After installing the conductor, we will continue drilling for a 20-inch steel casing and wellhead and cement and wellhead, and then cement it in place. On the right-hand side, we see what a wellhead installed in a conductor typically looks like. This is in a workshop environment, but try to imagine that this is the surface of the seabed. And what you see here is only what sticks up out of the seabed. And down below this is kilometers of or hundreds of meters of pipe. So up until now, we drilled in open water without a riser. But going forward, drilling will be conducted through a marine riser or casing that stretches from the rig on the surface down to the wellhead we just installed. So we were drilling without a riser, and as we drill, sand and water comes out of the hole and lands around. But going forward, we're going to drill deeper, and now we must drill with a casing riser. This casing riser, as I was just saying, is going to goes from the rig all the way up to the seabed, and is used in conjunction with a blowout preventer that gives us safety while we are drilling. So blowout preventer, or BOP, is now needed to contain the drilling mud and provide safety for the rig and environment during further drilling. With the casing riser and BOP installed, we now continue drilling. For the 14-inch casing, we cement the 14-inch casing, and we continue for the 10-inch casing and then also cement it. The reason you'll see that at each stage we cemented, it is actually cement, not our normal cement that we use when we are in construction, but it is a different type of cement, and it is used to seal the well as we drill and secure it. So without this cement, it would be possible that the oil and gas would travel around the casing that we are installing. The casing is being this pipe that we are installing until we reach the reservoir. So we cement around it to give the well safety, to cement it in place, secure the casing so it can't go anywhere, and it does not allow for any gas to flow around the casing. Once we're done installing the casing, we'll drill through again and install the production pipe. It will be through this production pipe and only through this production pipe that the hydrocarbons will flow up from the reservoir to the seabed. So we saw earlier the wellhead, and this is what a wellhead cross-section looks like, with a conductor housing in blue, with a pipe stretching down below it, and the wellhead sitting inside, locked inside the conductor housing with pipe, hundreds of meters of pipe perhaps, stretching down below it. And what does it do? It will locate the well and provides a connection point to the well and a seal for subsequent operations. So we saw the BOP earlier, the BOP here. This BOP needs to sit and lock on to something. And that is what the wellhead is for. The BOP sits on top of here, locks on, and seals so that anything inside of the casing cannot escape to the environment. Once we're done drilling, the Christmas tree and tubing hanger will also be installed on the wellhead. And this will allow us to control the production fluids after that. We see here several trees installed on what we see these large dark casings. These are the wellheads sticking out of the surface, and several Christmas trees located around a single manifold. So some considerations for the wellhead design. The wellheads need to survive the bending and vertical loads due to the drilling rig. As you can imagine, the drilling rig is up on the surface of the ocean, and we are drilling down 1,000, 1,500 meters below the surface. And the drilling rig is not completely stationary. It moves a little bit. It is able to try to stay in place through GPS, but it does move a bit. And the casing riser from the rig down to the well flexes. And so our wellhead needs to be able to survive the push and pull that is created by this casing riser. There's also the weight of the casing riser and the BOP, the water depths we need to think about, because there's hydrostatic pressure and the length of casing, the sea state, the currents in the soil, or how the soil is made up of, and what the actual casing program would look like. We take all of this into account when we design our wellhead. So we showed the BOP earlier that we need to use for drilling. And this is actually quite an important piece of equipment for drilling, perhaps the most important. This is what gives safety to our drilling operations. So this is a robust safety mechanism for drilling operations. It is run on the marine riser and landed on top of the wellhead that we just saw. The BOP stack provides multiple safety mechanisms to control the well. That includes rams, chokes, and kill lines. What these are different ways of closing the casing riser or closing the pipe so that nothing can flow up. If for any reason we need to stop pressure from below from coming up to the surface, the BOP allows us to close the pipe and nothing will come up. So casing riser and the BOP landed on the wellhead provide us a continuous conduit from the well to the seabed, on the seabed up to the rig on the surface. And this allows us to protect the environment. This is an example of what a BOP could look like on a rig. They're very large, very heavy. And that is how, and they have the several valves located, perhaps 7 of them, and they allow us to close the pipe while we're drilling. So on to subsea completions. We'll start with a Christmas tree. As we saw this image earlier, several Christmas trees landed on the wellheads, which help us control the gas coming up from the wellhead and flowing to a manifold. And then from here, they will go to the surface to onshore factory or to a floating LNG like the Coral. So a Christmas tree is an assembly of valves that directs and regulates the flow of hydrocarbons from the well. And the name Christmas tree comes from the shape and structure of the early trees. This was a question I had when I first started in the industry. Why do we call it Christmas tree? Because it doesn't look like anything like a Christmas tree. And it's because in the early days, this is what a Christmas tree used to look like on the surface. So the primary functions of a Christmas tree is to prevent the release of hydrocarbons from a well to the environment and direct and control the flow of hydrocarbons from the well. In the early days of offshore exploration, this is how it all started. When we started going off to sea on pontoons with the wells up here on the surface, and we've come a long way from here. You can see in the mid 1970s, we drilled in this was in shallow waters, and we had these subsea trees operated by divers. Today, we've gone deeper and deeper, and it is too deep for divers to go down. So our equipment, the subsea trees, have become more complicated. Today, they're operated by robotics and by computers, because we cannot send the divers so deep anymore. So our Christmas trees have evolved, changed shape, become bigger and bigger, and as we've reached deeper and deeper depths and higher pressures. And today, this might be what a vertical Christmas tree might look like. They can be, you can see they're much larger than they were initially, and these could weigh perhaps 40 to 70 tons of steel. And they allow us to safely extract the hydrocarbons. We saw earlier in the video a ROV, if you noticed, a robot underwater controlling some valves. And it is these valves here that the ROV operates. It'll have, because we can't send the diver down, it is done by ROV. And so the Christmas tree is designed so that a robot can come down and operate these valves. So some of the functions of the Christmas tree, they first and foremost provide safety and well control. They provide downhole communications to the surface control subsea safety valve. This is the first barrier below the Christmas tree that provides us safety. If we want to close the well for whatever reason, stop production or for safety, we can close the Subsea Controls subsea safety valve. The SCSSV is a mouthful. Downhole communications also to the downhole pressure and temperature sensors that tell us what is happening down below. Communications with the topsides. This could be, in the Coral's case, the floating LNG factory that is coming, or from Mozambique LNG, it would be a fungi. So from here, the umbilicals will connect all the way to either the floating LNG or to a fungi, and we can see what is going on and control. They give us annulus access. Annulus is the space around the production tubing. So if there's any need to inject something into the annulus axis to do some kind of operation, then the Christmas tree provides us with that access. The Christmas tree is equipped with a choke that allows us to control the downstream pressure. So we can control how much hydrocarbons we want to produce, rather than just allowing the hydrocarbons to flow under its own pressure. We are able to control how much pressure we allow to come out of the well. Christmas trees also allow us to allow for chemical injection. And this is needed sometimes when the hydrocarbons that are flowing out sometimes may cause some problems. They clog the Christmas tree or the pipelines, and these chemicals that we inject into the pipe, into the Christmas tree and pipeline, to free up the pipeline again to allow the flow of hydrocarbons to continue. Again, the top of the Christmas tree allows us to connect a BOP to perform operations, and these can be quite heavy, 40 to 90 tons. I've seen them that heavy. So more on safety and well control and how we do this. The hydrocarbons rise up from the well into the Christmas tree, and here they must go past several valves. But as a law, there's always two barriers to the environment. So between the hydrocarbons, the oil or the gas, and the environment out here, there's always two barriers. So these valves, the ROV tree cap, they serve as our barriers. So that we can never have the hydrocarbons escaping from the tree and into the environment. Further, these valves allow us to control the flow. If we want to, we can close the valves and close the production. Or through the choke further down here, we can, as I was saying earlier, we can control the pressure of the hydrocarbons. So the hydrocarbons flow from the well into the Christmas tree through these valves, and we can always see how it's flowing through the sensors we have on the tree. They flow through these valves down to what we call this U-loop. And from here, they will go to the manifold, and from there, they will go to the factory. So how do we install these Christmas trees? They can be installed from the rig, installation with a riser, but this takes longer, and during this operation, the rig cannot continue drilling. Or, as most modern Christmas trees can be installed on wire from a secondary vessel. This way, we free the rig to continue drilling the next well while we install the tree on wire. And this is faster, it's simpler, more cost effective. We see here, first the tree landing in the water and starting its trip down subsea. And finally, it'll reach the well, and the ROVs assist in locating the Christmas tree in the correct location and the correct orientation, which direction the tree will face before we land on the wellhead. And finally, below, we see the Christmas tree installed in the wellhead. So Christmas trees generally come in two forms today. They will usually be horizontal or vertical. They both provide the same basic functions that we just discussed, but offer different operational advantages. And it is up to the operator to choose which system will be more cost effective for them. Here in Mozambique, we will see both of them. Not these specifically that I'm showing now, but we will see horizontal Christmas trees and vertical Christmas tree systems, both here in Mozambique. In general, the horizontal Christmas trees sit directly on the wellhead, whilst the modern vertical trees sit on this tubing head, which in turn will sit on the wellhead. We see here on the right-hand side, the vertical tree is this top part here that our technician here is inspecting, and the tubing head is this bottom side here. And this tubing head sits on the wellhead. The hydrocarbons will flow up from the wellhead through the tubing head, here in the center, and into the Christmas tree, be controlled through the Christmas tree through the series of valves, and then will come out of this U-loop and out of here. And here will be connected to the manifold, which I will talk about next. So drill centers and manifolds. We saw earlier, what we typically see is Christmas trees we called clustered around a manifold. So multiple wells are feeding their production fluid, the hydrocarbons, into a single manifold. And this allows for easier, faster drilling for the rig. So when we drill, as we saw earlier in one of the first slides, the wells going down in different directions. We don't necessarily drill straight down, but we might drill at an angle. We can change the direction that we drill. So we will drill down, and then we'll start going off to the left, and we will drill almost horizontally until we reach the reservoir. But so each of these wells will be going to a different location on the reservoir that might be far apart, but we drill them all close to each other so that the rig can drill one well and then very close to it can start drilling the next well and so forth without it having to move much. This allows to save time. Otherwise, the rig would have to move perhaps a few kilometers away to continue drilling the next well. So Let's have a look at a actual example of a field in the Gulf of Mexico. This is just one drill center of several for this field. And we can see that this particular field has 20 Christmas trees clustered around 2 manifolds. And these 2 manifolds will feed 2 flow lines. These flow lines will then, as I was saying earlier, they will flow to the, say, a floating LNG or a rig or back to land, whichever the case may be for the project. In Mozambique, we will see for Coral LNG, the floating LNG, and for Mozambique, and for the Mozambique LNG, we will see these flow lines going back to Fungi. So without the use of these manifolds, in each Christmas tree, we need to have its own flow line and riser connecting it to the rig on the surface. So you see, each Christmas tree is landed on the wellhead on one well. The production from each one of these trees goes into the well, into the manifold. And from the manifold, it will flow to the flow lines, to just these 2 flow lines. So all of this production from 20 trees into 2 manifolds to 2 flow lines. If we did not have the manifolds, then each one of these trees would need to have its own flow line flowing back up to the rig. And this would add a lot of cost and complexity to the project. So in addition to receiving the flow from several Christmas trees, manifolds provide control over the production through valves and sensors, some controlled from the surface and some operated by ROV. Safety functions built into the computer on the manifolds will automatically kick in if needed. Finally, because the manifolds and flow lines themselves get dirty and clogged over time, the manifolds need to allow for cleaning. And this cleaning we call pigging. What we do during pigging is we push a chemical, usually called MEG, through the flow line, and it will flow from one end of the flow line all the way through the subsea field into the manifolds, and then out the other side, and then back to shore. And by doing this, we push all of the accumulated dirt that is inside of the manifolds or the flow lines. We push it out and we clear the pipe so that we can make sure that the flow continues unimpeded. So a quick overview again of the manifolds. They come in different shapes and sizes. They commingle the flow from several wells, usually into 1 or 2 flow lines. They come in 2 to 10 slot manifolds. As we saw here, these are 10 slot manifolds because they each receive 10 Christmas trees. And their branch sizes range from 4 to 7 inches, and the flow lines from 5 to 12, as this old slide says, but we can see as big as 22 inch. So between the Christmas trees and the manifolds, we need to have a connection that we saw in the video earlier. These are the well jumpers. So the well jumpers are pipelines required to bridge the gap for hydrocarbons between the Christmas trees and the manifold. They can be rigid, as we see here, or they can be flexible. They can be vertical or horizontal. In most cases, the jumpers will be just a simple, it'll be have a single pipe with 1 diameter, and this will allow just a flow of hydrocarbons. But in some cases, these jumpers can be more advanced and have more lines inside them, have a big pipe to flow the hydrocarbons and have small pipes inside it that will allow hydraulics and electrical communication to flow through the same pipe. In addition to connecting the Christmas trees to the manifolds, these also connect the manifolds to the PLETS, and from here, again, to shore or to the floating LNG. These are some examples. They come in different shapes. The most common shape is this M shape, and we see vertical jumpers and horizontal jumpers. And here we see a flexible jumper. some of these shapes, if we take, for example, this one up here, it might look, you might ask why they have this shape. This shape actually gives a rigid jumper some flexibility. There are currents underwater, and during installation, you need them to be a bit flexible to account for any error you make. So if they were just a straight pipe, they wouldn't have much flexibility. But by making a few bends on the pipe, say this like Z shape here, then it gives the pipe some flexibility. So connecting all of this equipment to shore, we have PLETS, PLEMS, ILTs, and sleds, and let's show that. So these are mouthfuls. So PLET is a pipeline end termination. For example, we see here, and they allow you to connect different sections of the subsea field. A PLEM is a pipeline end manifold, and really the only difference between a PLET and a PLEM is that the PLEM usually has more than one hub, a hub being this connection up here, and they typically have a valve that opens and closes. So if you wish to close production on a PLEM, you can do that. And a sled is also just used as an interconnection between two jumpers. So if you have a very long pipeline and you cannot build a pipeline that long, or it's too long to install by itself, you will use sleds in between. And the sleds look very much like a PLET, except they will have a U-looped shape for the connections. If we take here the example, we have two sleds shown here. Because this flow line is many kilometers and would be too long to have it in just a single pipe, we have the pipeline divided into two shorter pipelines that will start here at this PLET. It'll end at that sled and then continue again up to the rig. So it is just a connection between pipelines. So they take different shapes, as I was showing. I talked about the hubs. Up here, we see here a hub. This is where we make the connection for the jumpers. So you see here the jumper connected to a hub on this PLET and another hub on this PLET here. That is what we see there. That is what we see here. That is a hub. So these PLETs and PLEMs support valves and connector hubs. They support pig launching as well as I was saying, pigging, cleaning the wells, cleaning the pipelines, excuse me. They can also serve to commingle the flow. In some cases, instead of having a manifold, you will have a PLEM. And say in this case here, we have an isolated Christmas tree. And this Christmas tree doesn't connect to a manifold. It instead connects to a PLEM. Because it is out there on its own, it wouldn't be necessary to have a manifold there because it's just one Christmas tree. So we connected this lonely Christmas tree to our flow line by using a PLEM. We also sometimes have inline tees that will join the manifold into the flow line. And they can come in various slots. We saw here this PLEM that is used only to connect one tree, but we could make it with more slots. It effectively becomes a manifold, but it would just be smaller. So to control all of this subsea, all of this equipment on the seabed needs to be controlled. We have Christmas trees, manifolds, subsea processing systems, and they all need to be monitored and controlled to ensure the continuous and safe production. To achieve this, the Christmas trees, the manifolds, and the distribution systems include a computer called an SCM, or a Subsea Control Module, that looks like this. These complex computers allow remote monitoring of sensors and operation of valves on the equipment. These subsea control modules are connected to the topside control system on the surface platform by kilometers of umbilicals, hydraulic flying leads, and electrical flying leads. What we see here in this particular field in red, coming down from our floating production platform, we see this red pipeline, which is an umbilical. And from this, through this umbilical, our topside controls, our operators, are able to see everything that is going offshore by having it connected to the manifolds and the Christmas trees. So from here, they can provide electrical power, hydraulic power, and we are reading what the sensors on the trees and the manifolds are telling us. We can see the temperatures, we can see the pressure, we can see if valves are open or closed. We can see how much production we have on each of these trees and on the manifold. So this is done by the umbilical. And this umbilical will come and terminate on an umbilical termination assembly. And from here, we have these flying leads, these small connections in red that will go to the Christmas trees and the manifolds. And they provide, we have electrical flying leads and hydraulic flying leads that give us electrical and hydraulic power. Why hydraulic power? Because our valves work on hydraulics. They need oil and oil pressure to operate. So this oil pressure comes from this floating production platform through the umbilical all the way to our Christmas trees and our manifolds to operate them. So our primary purposes of controls is to provide power to the subsea field. This is supply hydraulic power to the control valves and electrical power to electrical equipment, the SCMs and other sensors. They send and receive status updates from the subsea field. The sensors provide pressure and temperature data, and the SCM transmits that data topsides in real time. Topsides is a term we use to meaning that our topside vessel, so our rig, our platform, our production platform, our floating LNG, whichever the case is. Control system allows us to open and close the valves, pull for data, and inject chemicals. So as we were saying, the Christmas trees have, and the manifolds have several valves with them that can control the flow. We can stop the flow, we can choke the flow, how much pressure comes through it, and we can do all of that from sending commands from the topside controls here on the vessel. Take a look at what the umbilical looks like. This is just an example. We can see we've got various chemical lines, hydraulic lines, electrical lines, all in one umbilical. And it is made of several layers that give it protection. The first layer giving it protection from, say, abrasion. And then we've got layers that give it strength and layers that contain the pressure inside it. And then various lines to give us hydraulic power, electrical power, distribute chemicals, and our fiber optics to control our equipment. Finally, as I was saying, besides the topsides controls, not every valve or necessarily every equipment is operated from the surface, from our topside controls. Sometimes we need to send a robot down there to operate the valves for us. Perhaps if the valve does not respond to our control, then we will need to do it manually, and we do this by sending an ROV. We use ROVs today because we are too deep for human divers. As I was saying earlier, we can be 1,500 meters deep and we can't send a diver down there. Divers go to perhaps 300 meters with very specialized equipment, and they can only spend a short amount of time when they're there. So when we go deeper, we use these ROVs, these remotely operated vehicles, to do the job for us. They're not autonomous. A human operates them. They don't go down. The human stays on the surface and operates them by a cable, and they do the job for us. So they assist us with the subsea operations. They have cameras. They have these arms and hands, and they can do the job for us. So I'm at the end of my presentation. The subsea field has many opportunities. We don't look for just technical roles. We require many support roles. I know some of you watching this presentation now and been listening are looking for this. How can you participate in this industry? How can you participate in these exciting projects that really are partly a future of Mozambique, really? We, for the next 30 years or 40 years or even longer, we will have need for mechanical engineers, electrical engineers, industrial engineers, welders, technicians, fabrication technicians in Mozambique, and other support functions that we need in our offices to make things run. Legal, finance and accounting, and human resources, logistics, trade compliance. These are very big operations. We install a lot of equipment. We have many vessels coming. And we are operating not just in Mozambique, but in several countries. These projects perhaps involve thousands of people throughout the world. And due to their complexity, we're not looking for just engineers. We're looking for all the support functions that go around it to make it happen. Thank you very much for listening. I hope you've enjoyed. I hope that I was able to show some of this equipment and it was interesting to you. Don't forget to visit the Mozambique Women of Energy channel on YouTube and see further videos there. In a particular case, say drilling. If you want to learn more about drilling, there is already a video there on that. It is very thorough. So don't forget to check out that channel to learn more about Subsea Field. Thank you, everyone.
Thank you, Michael, for this amazing presentation. Of course, we enjoyed very much, and I hope you all feel energized as I do after this presentation. And now we will follow with the Q&A session. We have many questions, and the first is from Nilza, and she is asking what type of Christmas tree will be used for the Mozambique project, vertical or horizontal, and why the choice?
So good question. The Mozambique LNG project will use the vertical system, and Coral is using the horizontal system. Why the choice can be very complicated to answer. It is usually up to the client, say Total or ENI, to look at how they want to conduct the operations and decide which type of tree they want to use. They both have some advantages and some disadvantages. Right off, the horizontal system is cheaper, and it is easier to install. And the vertical system is initially more expensive to start off with because there's more equipment, but it is cheaper to operate later on. Those are the main points surrounding the choice between horizontal and vertical systems. Then there might be some other operational issues that the client will have, depending on what rig they want to use and what equipment they already have and what experience they have, that will help them decide if they want to use horizontal or vertical systems.
Thank you for the answer. The next question is from an attendee that is not identified, and he or she is asking how many projects do you have? How many projects have you worked on, and what are the main difficulties did you face it in?
So I've worked on a few projects since I started in the industry, in the United States, in Nigeria, and in Ghana. And I wouldn't say difficulties. I would say you have to learn to focus on quality and in safety. You saw this equipment is very big. You need to achieve a very high quality to operate successfully, to make your client happy, and to not cause obviously any damage to the environment. So you need to always focus on quality and safety, and there are absolutes in this industry. And that starts when you are in the workshop assembling the equipment. For example, assembling a Christmas tree. You've seen that the equipment is very heavy, and there is a lot of testing involved with the equipment, pressure testing. So you always focus on safety and you focus on quality and you insist on it.
Okay, the next question is from Vanessa Valente, and she says, first of all, I want to thank you for this presentation. What are the main challenges that the environment offers for the drilling operation?
The depth of your well, and then the depth of your well yourself, and the reservoir, how and what you have to drill through. You are drilling down to 1,500 meter depth with a vessel that is located by GPS, and the sea is moving, and under the sea surface you've got different currents that are pushing your pipe around as well, and all of your equipment needs to survive that.
Okay, and another question from Vanessa Valenti. She is asking, as pigging is a routine operation, is there any time frame to do it? She wants to know how often the pigging operation is done in a facility.
It ought not to be a routine operation. It is an operation that needs to be done from time to time because you get the line clogs. So I cannot tell you how often it is done, but it is you could say it's an operation that is very common. Operators know how to do it. The equipment is designed to be able to allow us to do it, but you don't want to get to that point. You want to try to prevent a situation where you need to do pigging. When you need to do pigging is because you're not flowing anymore. And before then, you're going to put chemicals into your flow line, into your Christmas tree, chemicals that will dissolve whatever is any solids that are in there. So pigging is a last resort because when you do pigging, you need to stop producing oil.
All right. And another question from an anonymous attendee. He or she is asking, what is the sequence of installation of manifolds and other subsea equipments?
Can you repeat that question, Márcia?
He or she is asking, what is the sequence for installation of the manifolds and other equipments?
Typically, you will drill the wells. You will install the Christmas trees on the wellhead, and you will install the manifold after that. But it doesn't have to be. You can install the manifold and then install the Christmas trees. You don't have to follow a sequence. It depends on, it could be which one is available first. The Christmas tree finished production first and is available to be installed. It could be the schedule of the vessels. The vessel that installs the Christmas tree is not necessarily the same vessel that installs the manifold, because the manifold is much heavier than the Christmas tree, much bigger, much heavier, and you need a much stronger crane to install it. So it is an operational decision which one you want to install first.
Mm-hmm. And now a question from my side. I have a curiosity. I would like to know what are the main aspects to take into consideration to select subsea equipment for a certain project.
There was a question about horizontal and vertical trees. It is CapEx versus OpEx, our initial costs versus our project costs. the depth of the field, what you are producing. Are you producing oil or gas? And the quality of it. What are the pressures involved? Some you might have a production pressure of 100 bar, or you might have a production pressure of 600 bar pressure. And so your equipment is designed for that.
All right. Another question is from another attendee not identified. He or she is asking, what are the type of maintenance expected on the equipment installed in seabed? How long is the normal lifespan of the overall subsea system?
The equipment is typically designed for the life of the project. So you can imagine the seawater is very corrosive, but our equipment has what we call anodes, aluminum anodes. And so with these anodes, the equipment is designed to survive 30 years of operation without interruption. Other equipments that perhaps don't survive as long, it is some equipments every 5 years, they go through a recertification process, but not our manifolds or Christmas trees. Those are usually installed and they stay there until we're done with the project, until we are done producing. And after that, we might remove the Christmas tree and plug and abandon the well. But subsea permanently installed equipment, it must last the lifetime of the project. So 30 years or more.
Okay. And Nilsa is asking, what is the next for the subsea engineer after the installation for the subsea equipment is completed and the wells are handed for production?
Once we're done installing, we need to maintain it and continue to support the client. So ideally, the production will continue flawlessly for the next 30 years, but it's not always the case. And any time that the client needs to access the well again or do any operation subsea involving the equipment, they will call back on us that designed and built the equipment. They will call on us for support. So throughout the next 30 years of the project, you will always have engineering support to ensure that the continued life of the equipment, that it doesn't have any problems. Anytime that work needs to be done on it, it is done correctly and safely. And so we never stop supporting the customer.
A question from Barcy Horacio. He says, hi, Michael. I really enjoyed the presentation and thanks for sharing. I have a question. What are the typical challenges that can emerge during the subsea installation phase?
Difficult for me to answer that one. I believe that will be in a later presentation with our subsea installation engineers. But you might have issues installing any of our equipment, if, for example, installing a Christmas tree or a tubing head or a manifold. Sometimes things have been landed in the wrong place and you discover that later. These things happen, or sometimes something falls. You lose some equipment and you need to go and find it somewhere on the seabed. These things can happen.
Okay, and Vanya Coutinho says, hi everyone, I'm here just to congratulate the speaker, the introducer, and wish success in his career. We are part of this industry, and now it is a pleasure to be surrounded by experienced people like him. Of course, we are very happy to have you as our guest, and I want to say thank you, Michael, to accept the invitation to be the finalist today. And we have another question. Someone is asking, what is the most complicated project you have worked on? what is the most complicated project you have worked on?
Most of my experience is right here with the Mozambique LNG. So this would be the most complicated project I've worked on. It is a very big project, 20 Christmas trees, 7 manifolds, and tons of equipment to install. We have a list of over perhaps, let's say, 2,000 different pieces of equipment that will be installed or are tools that will help us install. So there's a lot of equipment to know, a lot of procedures to be familiar with, and a lot of maintenance to be done on all of this equipment too. Not only do we do maintenance on the equipment that we install, but all of that equipment that helps us install the Christmas trees and the manifolds and everything else that goes to the seabed. All of that equipment needs to be maintained as well. So, and we will continue that for the next 30 years.
Okay, great. Unfortunately, we don't have much time, so I would like to ask a question to finalize. I would like to know from you, what advice do you give to young engineers that aim to work as a subsea installation engineer?
Be excited about it. Prepare yourself for a demanding industry. Read up on it, understand the equipment. Well, you don't have to understand the equipment because you're not in there yet, but educate yourself. Work hard at engineering and apply. Come to us. We are always looking for excited engineers.
Okay, thank you for this advice. Thank you once again for accepting the invitation for this amazing presentation. I hope you all feel energized, and I would like to say thank you all the attendees for joining us today. Stay tuned in our social media, and we will update you for the upcoming episodes. This is MFWE, Mozambique Women of Energy, a platform for women, and we want to raise the voices of all the Mozambican women in the energy sector. Thank you. Goodbye.
Thank you, everyone.